Assalamu alaikum, sir. My name is Nazm Saqib and my ID is 23508661. Well, this course name is Digital Logic Circuits, and today I'm going to discuss about the final term assignment. So here given total 8 variable from A to H, and I have put the value according to my ID number, and in the instruction related to variables it has been said that if there is any zero in the ID number, it has to be replaced by A plus B plus H. So I have replaced it and put it into D, since my value in D is 0. Well, let's move on to the assignment questions. Our assignment topic was to design a system related to hospital ICU bed monitoring and control system. So where B plus F plus H number of patients can be admitted, and the number of B plus F plus H is 10. So in ICU there could be 10 patients at once could be admitted. So in the task section, in question 1, it has been said that we have to draw a block diagram and flow diagram of the automated ICU bed monitoring system as describing above in the questions, and I have to show the internal design of the counter, such as how the flip-flops are used to design the counter. So let's move on to the answer of question 1. Earlier I have discussed already that our max patients capacity in ICU ward was 10, so there was 10 bed. So we know that binary of 10 is 1010. Now steps for designing an automated ICU monitoring systems are here. In step 1, we can take input to the encoder by using the keypad. The input in is then encoded using keypad by a 16:4 encoder. So here is the design from I0 to I15, and our output was Y0, Y1, Y2, Y3. This is a 16:4 encoder, so this is the block diagram for the encoder. So now if I draw the truth table for the encoder, here it is look like this, and I can now put the values in the output, like from the truth table I found out Y0 equal I1, I3 I1 plus I3 plus I5 plus I7, Y1 equal I2 plus I3 plus I6 plus I7. So here it is like this, and now in the circuit diagram, putting all those values, we have taken here actually I0 to I8 because our value was 1010. So before that we took we took the output value from 1000 because the last value where the 1 is given in Y3, it's actually 100. So now we are drawing the circuit diagram and putting the output value here. So this is the design. Now in this step 2, we have to actually showcase the sensor to display block diagram. So here I'm showcasing that patients are admitted, and another one is patients are discharged. So it can be counted by the counter. So it is gone through by 4-bit up down counter, then 4-bit parallel in parallel out register, then 4-bit comparator. So after 4-bit comparator, if the count is equal to 10, then the 555 timer will show the display to full. But if the count is less than 10, then the 555 timer 2 will display the ICU beds are available, and it will blink. So in the flow diagram also, here also the similar thing, but a slight change. With the counter, we have starting counter from 0000. It is given to the sensors. Then if the patient is admitted, then it is an entry. So and count is count plus 1. And if the patient is discharged, then it is an exit. So the count will be count minus 1. So we are comparing the beds until count equal to 10. So again the same thing, count equal 10, the display will be shown to full, and if the count is less than 10, then the display will be beds available, and that's the end. And after it will repeat from the sensors again. So in step 4, I have to draw the 4-bit synchronous up down counter. We'll be using JK flip-flops for counting because it has toggle mode, and we know that J equal K equal 1, which is the most efficient way. First, let's draw the state diagram. So we can see in the state diagram, so we assume that here M equal 1, so it is like counting from the upside, like the clockwise direction, and if it's the downside, it will be anti-clockwise direction, like 0 0 0, it will count like that. So we started from 0 0 0 0, and we have finished our counting from 1 0 1 0, because that's our total bed in the ICU ward, that is 10. Then we have drawn the 4-bit synchronous up down counter, which is like this. We have used 4 JK flip flops, and then we have connected it through the AND gates and OR gates also. And from the first JK flip flop, we have put into the shift load. We have used the shift load method, and then here we have used a clock, and we have connected that clock to every JK flip flop. So we have found the equations: J naught equal K naught equal 1, J1 equal K1, which is M Q naught plus M bar Q naught bar, from this 4-bit synchronous up down block diagram. So in step 5, now the up down counter is connected to a 4-bit parallel in or parallel out PPO to hold the counter values. So this is the parallel in parallel out diagram, you can see. So in step 6, here is also one thing that we have given the input like data not data 1, data 2, data 3 from the upper side all at once, because it is a parallel input, and also we have taken the output simultaneously all at once, like Q0, Q1, Q2, not like there are other counter like PISOs, CISO. So in step 6, now value of A is fixed, which is, we know that already, A equal 1010. B will be collected from the register. We need a 4-bit comparator to compare A and B. So here is the design. We have drawn the comparator. So from A0, B0 to A3, B3, we have connected all this, and here is two output, G1 and G2. G1 is if A is greater than equal B, and G2 is if A equal B. So in step 7, now this output G1 is basically get 1. Will direct to the 555 timer and display bits available, and get 2 G2 will direct to another 555 timer and display full. Here is the block diagram of the comparator. This is the computation between the comparator and the 555 timer. So that was the answer for the question 1. That is the process I have done. So let's go through the second question. In second question, it is asking that we have to design a circuit where two 7-segment displays with two 555 timers. So there will be two 555 timers, one for full and another for the bits available. If all ICU bits are filled, then it should display the word full. So when bits are available, it should blink out the words bits available. So here are the rules we have to follow. We have given some data like a frequency F equal A plus C plus Z, and the display will be on for TH, like TH into microsecond, and off for TL. So let's go through that. So in part 2, we have already calculated the parameter for the bits available, that P equal A plus B plus D plus E plus G into 2, which was given, and I have put my ID value into it, and getting the value P equal to 50. So we know that duty cycle D equal 100 minus P, so duty cycle was 50%, and frequency was F, which was A plus C plus 5, so it was 12 Hz frequency, and the time period T equal, we know that 1 by F, so it was, after calculation, it was 83.33 microseconds, and thus the time period for high equal duty cycle into T, so it was like 41.67 microsecond. So, and we also know that T is equal to TH plus TL, time period high plus time period low. So after calculating, we have found out the TL from here, which is also 41.66 microsecond. So now, it has been given that the question that we have to choose an appropriate resistor value to generate the output with required duty cycle. So we have to select a capacitor. There are already given 3 capacitors, 50 microfarad, 250 microfarad, and 470 microfarad. So if I need any other sequential or combination logic components, so I could be adding there, and I have to provide the justification for this use. So let's go through it. So now for capacitor 50 microfarad, I have calculated the time high and time low value, and and from there I have found out the register 2 and register 1 R2 and R1, which was pretty similar. And from there I have found out the register 2 and register 1 R2 and R1, which was pretty similar R2 and R1 for 50 microfarad, which was 1.20 kilo ohm, and R1 is also 1.20 kilo ohm, so they both are same. So now let's calculate the capacitor, which value was 250 microfarad. So after calculating, we find out that it is pretty low. We have found out the value for R2 is only 240.46 ohm, and from previous value we have already get a kilo ohm, so huge difference. And R1 for capacitor 250 microfarad is 0.0595 ohm. So after we also calculated C equal to 470 microfarad. So also it is very low from which I have gotten for the C equal to 50 microfarad. So that's why we are going to choose capacitor C equal to 50 microfarad, because in terms of resistance for 250 microfarad and 470 microfarad, values of resistance get very low. So choosing 50 microfarad capacitor will be safe. So here's the stable mode for 555 timer. It's the design for 555 timer. We have chosen that stable mode 555 timer for the bits available, because in the question it was asking that we have to show that when the bits are available, it should be blinking in the 7-segment display. So that's why we choose the stable mode. And here we can see that we have chosen the 50 microfarad capacitor, and we have put the 1 kilo ohm resistor for both the resistance. And in the third pin, it is showing the output. The first pin is basically the ground, second is trigger, 6 is the threshold, 4 is reset. And here we have used another capacitor, but it is mainly optional. So next we have used bistable mode 555 timer. So here we have only used a single resistance. Here we have used trigger, threshold and discharge. So we have used basically bistable mode here, because when the counter will be hitting to full, like equal to 10, so it will show full but it will not blink. So as the output should continuously display full, that's why we are using 555 timer as a bistable multi-vibrator, and using the comparator output to drive the reset pin number 4, which is here, to hold the output high. So if the output is high all the time, so there will be no blinking, and we will continuously display that the bits are full for the IC word. So thus the comparator output is connected to the 555 timer, where the input is high, so the timer output is held high continuously. Additionally, we may use counters to track the number of bits. Then 4-bit PIPO register is used to hold the counter values, and finally we use comparator to compare and trigger the timer display. So in part 3 we have to design an FSM, finite state machine. So for output A, there are time high microsecond, and then the output B is time low. So here the clock period is 1 microsecond. We have to show the state diagram, state table and Verilog HDL code only for the outputs A and B. So here are some notes that if the time high and time low is greater than 4, then we have to set it to equal 4 for both. So getting in the answers part, in the FSM design, we have already taken the value that clock period is equal 1 microsecond from to TH equal 41.67 millisecond, which was found from the second part, and time low is also 41.67 microsecond. So since these both are greater than 4, then we have set that time high equal to 4 microsecond, and we have also set time low is equal to 4 microsecond. Now FSM state diagram design. So we have started from the reset 000, then we have gone through 001, 010001 to 111. So there are basically 8 states. So in the state table we have taken the reset value. First it will be from 1, then after press once, then it will go to 0. And in the present state there are also we have taken the 3 inputs like present state not, present state 1, present state 2, and then for the next state there is next state 0, next state 1, next state 2, and we have taken the 2 output, which was A and B. So we have done that in the state table here. That in the present table state table transition, that in the first row we can see that this present state is 000, which and after that the next state value is basically the next row value of the present state, which is 001, and it will go to the next state. It will go to the first row of the next state. And similarly, after going to the last row, when there is no next row, we have basically taken the first row of the present state and put it in the last row in the next state, and we have find out our output here. So here is the Verilog HDL code for the outputs A and B only. So we have commented out that for the finite state machine, outputs A for T high equal to 4 microsecond, and for B it is also 4 microsecond, and total state is 8. So after the code is actually start from here, module FSM outputs. We have taken the input clock. We have also taken the input reset. So there is the 2 output register A and output B, HB. So this output register B. So here are basically 3-bit state register for the 8 states. Register 2:0 state. So state transition will be happening for synchronously with reset. This is the code syntax. Always at the rate positive age clock or positive age reset begin. If reset that the state is less than or equal 0, or else if state equal 7, then state is less than equal 0. So here's the output logic I found out, and we have found out that if state is less than equal 4 begin, then output for A equal to 1-B1 and for B is equal to 1-B0 for the on phase, and this is for the off phase if the on phase is not happening. So for the part 4, basically it is telling us that we have to find out the drawbacks or limitations for the part 1 and 2. So we have designed the block diagram and flowchart for the hospital management system, ICU bed management system, and we have to find out the drawbacks and limitations. So what modifications can be made to the system to employ it in hospitals with a higher number of ICU beds. So we have to also analyze the specific change on the system, if there are any impact if the system design will be changed. So let's go through the part 4. So we have found out many drawbacks for the part 1, that it has the fixed capacity, like a hardware for 10 bits, our system design. So changing the capacity required full hardware redesign. So if there are 50 bits or 100 bits or 200 bits, then we have to change the full hardware redesign. So there will be wider counter and new computer also. So there could be sensor glitches. So basically it is mechanical sensors will produce bounce pulses. So, and we know that without debounce circuits the counter may overcount or it could be undercount. So it is a drawback also. So in the simultaneous events, concurrent admission and discharge, if the admission and the discharge is happening simultaneously, so the pulses have no priority logic, so undefined counter behavior could be triggered. So it is also a drawback. So no occupancy readout, system only shows full available, not the actual count. If the like it is 10 or 15, whatever the value for the maximum bit is. So it's a drawback for reducing the information for the clinical staff. Single keypad entry. So we have seen that max capacity entered once, no input validation against invalid or out of range values. That max capacity was 10, so we cannot put any other input validation here. So for the 555 timer circuit, there are some drawbacks, that it has no enable pin. 555 timers cannot be paused or held. External D flip-flop latching is required to hold display state and adds component count. So component tolerance, like resistor and the capacitor values have manufacturing tolerances from plus minus 5 to 10%, causing time period high and time period low to deviate from calculated values, affecting duty cycle accuracy. Also, there could be frequency drift. The 555 timer 555 oscillator frequency drifts with temperature, leading to slight variations in blink rate over time. Not scalable. A separate 555 timer is needed for each display mode, adding more display states, warning at 80% capacity. That a separate 555 timer would be needed for each display mode. So there could be requires additional timers and logic. If I could show another something more to the display, then I have to use another additional timers. That is what it was talking about here. So finally, power consumption. In the power consumption, continuous oscillation of the 555 timer draws quiescent current even when not needed, increasing system power consumption. So it would basically draws current which is not needed, so it increases the system power consumption. Modification for higher ICU. So that's the last part. If we suggest some modifications, so here are some suggestion for the modification. That specification change. If the hospital wants to monitor more than 10 beds, for example 50, 100 or 20 beds, so required modification would be wider counter. A 10-bed counter uses 4 flip-flops. For 50 beds, 6 flip-flops, 2 to the power 6 equal to 64. For 100 beds, 7 flip-flops. For 200 beds, 8 flip-flops. More D flip-flops stages are required. Programmable comparator would be needed, like replace the fixed hardware comparator with a programmable digital comparator or magnitude comparator. IC integrated circuit like 74HC85 would be recommended because it accepts the max value from the keypad dynamically, allowing capacity to be set in software, not in the hardware part. So it would be a flexibility. Wider keyboard binary coded decimal input, which is the keyboard input must encode larger values, multi-digit BCD with additional decoding logic and registers, not for 0 to 9 or 0 to 10. Microcontroller replacement. For very large capacities, 100 plus bits, replace the discrete logic counter and comparator with a microcontroller which can handle arbitrary bit counts, real-time display and network connectivity. So that's why the replacement would be needed. And the impact analysis part, hardware complexity increases, more flip-flops, more complex comparator logic are required, increasing PCB area and component cost. Power consumption increases, more logic gates and flip-flops draws more quiescent current. So basically, if I use more logic gates and the flip-flops, it would draw more current which is not needed actually. So it will increase our power consumption in the circuit, in our system. In the propagation delay, it would be increased, like wider counters and comparator have longer combinational delays, so potentially requiring a lower clock frequency or pipeline design. Display upgrade needed. Our display must be updated because a 7-segment display can only show 7-segment display can only show 10 digits at most. For 100 plus bits, a multi-digit LED or LCD panel is needed. Robustness improves. A microcontroller based system can include error checking, logging and network alerts, significantly improving hospitals' workflow. So these are the things which would be, if added in the hospital ICU bed management system, that the impact would be much better in my opinion, and that's why I have put it all in here. So as per requirements, I have put my name and ID in the middle of the paper, in the middle of the script in each paper. Here is one missing. That's it for our assignment. Thank you, sir. Thank you for giving me this opportunity. Assalamu alaikum.